Hello from the Northwest School. This is an instructional video from the physics class on constant velocity motion. Let's get started. First, some terms to describe the motion. Position. The position is the location of an object relative to a coordinate system. Here we have a one-dimensional coordinate system with two bicycles. The red arrow indicates the origin of the coordinate system. The green bike has a position of 4 meters to the right, or 4 meters east, or we might call it just plus 4 meters. The blue bike has a position of 1 meter left, or 1 meter west, or negative 1 meters. Different conventions are used to describe the position of objects depending on the problem. The next two terms are displacement and distance. It is easiest to show these with a diagram. The figure here shows that the distance is along this line here, is the actual number of meters, feet, or miles traveled between 2 points A and B, while displacement is the straight line measurement. Displacement is always defined as the final position minus the initial position. Another example here shows several buildings on a horizontal line. A student starts at the dorm and then walks to the physics building and then turns around, walks back past the dorm to the cafeteria, as shown by this green line. The distance is 5 blocks because that is how many blocks the student covered. 2 in this direction, another 2, and then an additional 1 in this direction makes 5. The displacement is negative 1 block because the student ended at 1 block to the left of where they started, as indicated by the red arrow. In class this week, we made measurements of position as a function of time for a constant motion vehicle. Here is some sample data with time on the horizontal axis and position on the vertical axis. The graph does not start at 0 because the car did not start its motion at 0. We can find the equation of the line that describes this data, which is then useful to predict future locations. I click and drag on the data and go to linear fit. The results of this linear fit are here, and I'll put them in our screen over here. Now we can use these results to find the equation of the line. We're going to use the basic equation of the line y equals mx plus b. But now we'll use the results from our linear fit. The number here circled in blue from the linear fit gives us the slope of the line. The slope of a position versus time graph gives us velocity, 7.086 centimeters per second. The b value, the y-intercept, is 18.29 centimeters. That's the starting position of the buggy relative to 0. So the final equation that describes our variables is this one here. P equals 7.086 t plus 18.29. Notice that I have replaced the variables y and x with p and t. It is important to write the equations in terms of the variables with which we are working. Now that we have the equation that relates position and time for the tumble buggy, we can use that equation to answer some questions. First up, what is the position of the tumble buggy at 3.5 seconds? Have an idea how to do this? I'm sure you do. Since we are given time, we plug in 3.5 for t and then solve for the position. You can see the results here, and also how to follow along over here if you wanted to include the units. Sometimes that's clearer for some people. Next question, how long does it take the tumble buggy to arrive at a position of 1 kilometer? This time we're given a position and need to solve for time. But watch out for units. Our original equation is in terms of centimeters, so we can't just substitute 1 kilometer into the equation. We first have to convert from kilometers to centimeters. Then we can plug in 100,000 centimeters into our equation here and solve for t. When we finally solve for t, we get a very large number of seconds, which makes sense because it will take the tumble buggy a while to reach a position of 1 kilometer away from where it started. So this comes out to be 3.91 hours, but probably the battery won't hold up. Now it's your turn. Here's a sample problem for you to try. The following 3 questions refer to the data taken from this other tumble buggy. You'll notice that the graph here looks a little bit different than the one we were first working with. Do you know why? The information from the linear fit for this data is here. You can pause the video and answer these 3 questions. When you have answers, restart the video and check your work. Hopefully you stopped the video and figured out the answers to the questions. Here's the equation that relates position and time for this vehicle. The slope is negative, this number, minus 9.20t, because the car is moving in the opposite direction as the first one that we looked at. It also has a larger value, which means that that tumble buggy was moving faster than the first one. This tumble buggy is moving in the opposite direction and moving back towards the origin of the coordinate system rather than away from it. For number 2, the position of the tumble buggy at 10.2 seconds was 26.69 centimeters, and the time for the tumble buggy to reach position 0, or the origin of the coordinate system, is 7.10 seconds. That's all for now. See you in class.